Okay, so 2-1 is inductive reasoning to make conjectures, because the title of this, like I said, is reasoning and proofs. So you might also think of it as logical thinking, logical reasoning. And we're starting with inductive reasoning to make conjectures. So you would need to know what is a conjecture in order to use inductive reasoning to make a conjecture. So a conjecture is a statement that is believed to be true. So believed to be true. Notice I didn't say that it is true. I said it's believed to be true. So an example would be if I made the statement that every prime number is odd. That's a conjecture. It's a statement that is believed to be true or not. Similar to a prediction or a hypothesis, if you want to go into science, branch over, it's the same thing. This is the hypothesis, sort of, from a science experiment. Whatever you believe to be the outcome, whatever you believe to be true, you make a statement saying that. Then you or someone else could make a counterexample if they think that your statement is false, your conjecture is false. It can be proven false with a counterexample. So an example that proves a statement is false. So my conjecture, every prime number is odd, can be proven false with the counterexample that 2 is prime, but not odd. 2 is the only even prime number. Prime is, it can only be divided by itself and 1, just to be clear. And then the third term is inductive reasoning, and that's the type of reasoning we're going to go over for geometry. You know, if you know anyone in pre-AP or in honors geometry, they are also going to be using deductive reasoning. So they're going to have 2 types of reasoning. So don't get confused if you work with someone from one of those classes. They are doing 2 different types. We're just using inductive reasoning. And that is the process of reasoning that a rule or statement is true because specific cases are true. Okay? So examples. Inductive reasoning is reasoning based on examples, where the other type, the deductive, is based on work, like previous steps of showing your work kind of thing. We're doing inductive based on an example. So it's not necessarily going to be a math conjecture. You know, I make a conjecture that it's going to rain today. And then if it doesn't rain, then I guess that's the counterexample. But anyway. First example, make a conjecture about the next item in the pattern. So, yeah, it is July because you have January, and then you don't say February, March, April, May, June, July, every other month. Following the pattern, there's my conjecture or prediction of what's next in the pattern. 7, 14, 21, 28, 35. This is adding 7 every time. 7 plus 7 is 14. 14 plus 7 is 21. 21 plus 7 is 28. 28 plus 7 is 35. Or something simple like this. I like simple examples and problems, especially since this is geometry and that's a triangle. Alright, so if this is the pointy part of the triangle, it's going up, and then now it's over here on the left, and then it's down here on the bottom. Where's it going to be next? To the right. It can be that simple, just predicting what's next in the pattern. This one's a little trickier. 4, 5, 9, 14, 23. All right, so if we take 4 plus 5, that gives us 9. And 9, oh no, 5 plus 9 is 14. And 9 plus 14 is 23. So then 14 plus 23 gives us 37. So my conjecture is that will be 37.
So basically it's just guessing this one. What do you do? Educational guess?
Exactly, an educated guess. Predicting what you think is going to be next. A true-false statement. It might be false. Hopefully it's true. You're shooting for a true statement, but it could be false. All right, the next type. Complete the conjectures. The number of lines formed by 4 points, no 3 of which are collinear, is what? So before we just take a guess, remember I said we're doing conjections based on examples? So we need 4 points and 3 of them cannot be in the same line, right? Collinear, remember that root word there? Line. So they're on the same line. So we can't have 3 on the same line. But we could have 1, 2, we could put one over here. We could put one, I don't know, let's do it over here. That works. There's 4 points. And how many lines or line segments can they make? Well, clearly we can connect the dots going around. So there's 4 lines. Can we make any more lines? Yeah? We go across. So our conjecture would be 6, right? We can make 6 line segments between 4 points as long as no 3 of which are collinear. So you just make up an example. The sum of 2 positive numbers is blank. All right, so 2 positive numbers.
Any positive, right?
Yeah. 1. Sure, 1 plus 2, that's 2 positive numbers. It's 3. Let's go and do one more.
15.
Okay, 15 plus 20. That gives us 35. That's positive. We have ended up with 2 positive outcomes. So let's just go ahead and make the conjecture positive. The sum of 2 positive numbers is positive. That's a conjecture. All right, so then the product of an even and an odd number. So even 2 times an odd number, 3, that's 6. And then 4 times 5, that's an even and an odd, that's 20. Both of these came out to be even. So it's a pretty safe conjecture that the product of an even and an odd number is even.
It's like positive plus positive plus negative, right?
Sorry, what?
Like positive number plus another positive equals negative, right?
No, we just did that on example B. We're doing multiplication now and talking about odds and evens. All right, part D. A rule in terms of n for the sum of the first n odd positive integers is what? Okay, so this is a little confusing. But sometimes confusing examples can be good too. I'm going to zoom in. So we want the first n odd positive integers. So n is like the number of, like how many. So I'm going to make a table. N. And we're just going to do 1, 2, 3, 4. And this number n is representing how many odd integers. Okay, so for 1, the first odd integer, so this is integers. All right, so the first odd integer is 1. And then the first two odd integers, 1 plus 3. And then the first three, 1 plus 3 plus 5. And then the first four, 1 plus 3 plus 5 plus 7. And 4 is enough. We don't need to keep going because we're just making a conjecture. We're not actually trying to prove it. We just want a best guess. And it said the sum of them, right? So what we're going to be doing, actually, let me do that, is we're going to compare n with the sum. Okay? So 1, the sum of 1 is 1. There's nothing to add there. 1 plus 3 is 4. 1 plus 3 plus 5 is 8. 9. Sorry. 9. And then 1 plus 3 plus 5 plus 17 plus 7. Oh my goodness. 1 plus 3 plus 5 plus 7 is 16. So if we compare the first column n with the last column, the sum of the numbers, do you see a pattern? 1 to 1. 2 becomes 4. 3 becomes 9. 4 becomes 16. It's a familiar pattern, right? These numbers 1, 4, 9, 16. Those are the squares, perfect squares. So we could make a conjecture or a rule that says a rule in terms of n for the sum of the first n odd positive integers is n squared. So whatever the n number is, if you square it, you get the same thing as you get the result of adding up the odd integers. Just a neat little thing. That's pretty complicated. I understand that. I'm not asking you to do something like that on your own, so don't get worried. Okay? We're going to keep this simple. All right. Next example. Show that the conjecture is false by finding a counterexample. So this next part, we want to prove that these are false, or say that they're false with a counterexample. For every integer n to the third is positive. So if we want to say that that's not true, we need an example. So we need a value of n that if we raise it to the third power, it's going to give us a negative number.
So if n was negative, then it would be...
Yeah, if n is negative, then it works. So what's a negative number? Any. Sure. I'm actually, just because 1 is a special number and 1 times 1 times 1 is 1, I'm going to go with the next one, 3. Well, it's not the next one. I guess I said 2. Yeah, let's go with negative 2. It's hard to see a pattern with 1, so let's go with 2. What if n is negative 2? Now we have negative 2 to the third power. If that was negative 2 to the second power, it would be negative 2 times negative 2, and so it would become positive. But this is to the third power, so it's negative 2 times negative 2 times negative 2, so that's negative 8, which is negative. All right, all prime numbers are odd. If I want to say that's false, I need a counterexample, which I already did this one earlier in the table. 2. Because 2 is prime but not odd. And C. If the product of two numbers is even, then the two numbers must be even. All right, so what's the product of two numbers that are even and one of them is not? One or both. All right, so an odd number. 3. 3 is an odd number. 3 times something that's going to give us an even number. Well, 3 times 2 gives us 6, right? 3 times 2 is 6. The product of two numbers is even, then the two numbers must be even. Well, 3 is not even. So I just disproved the statement, the conjecture, by using a counterexample. All right, so the next part. Determine whether each conjecture is true or false. If false, give a counterexample. All right, so we're deciding if it's true or false now. Last time we were told they were false. If points A, B, and C are collinear on the same line, then AB plus BC equals AC. All right, well, first let me draw that out. That points A, B, and C are collinear, and here's an equation. So I have 3 collinear points. And since it equals AC, then I know this is A, and this is C, and B must be in between them somewhere. So then AB plus BC equals AC. The left piece plus the right piece equals the whole thing. So if points A, B, and C are collinear, then AB plus BC equals AC. Is this true or false? It can be true, but what if we have points A, B, and C, and we have B, C, A. Aren't those points collinear? Does AB plus BC equals AC? That's saying the whole thing plus part of it equals part of it. That doesn't make sense, does it? So this is false. Because the statement can be true, but it's not always true. All right, so then the next one, if angle ABC and angle DEF are supplementary, then angle ABC and angle DEF form a linear pair. All right, so we know that supplementary means they have a sum of 180 degrees. And then form a linear pair. What sum does a linear pair have? What shape does it make? A line pair, right? So a pair of angles that make a line. So a straight line also has a sum of 180 degrees. But is every set of supplementary angles a linear pair? No. Because a linear pair, it does have a sum of 180, but it also must be a pair of angles, so 2 angles. And those 2 angles must be adjacent. Remember, adjacent means right next to each other. They share a side. So a pair of angles that make a line. All right, so here, an angle right there, and another one right there. So we have 2 angles that make a straight line. That's a linear pair. There's 2 of them, and they share a side. Supplementary angles, that could be any number of angles as long as they add up to be 180 degrees, and there's no restrictions on their relationship. They could be next to each other, they could be apart from each other, turned one way, turned another way, it doesn't matter. As long as the supplementary is just focused on the sum, a linear pair, the sum is just part of it. So this is also false. Because angle ABC and DEF could have a sum of 180 but no common side. And based on the letters, it doesn't sound like they have a common side. So angle ABC and angle DEF could have a sum of 180 degrees, but no common side. All right, and that concludes the notes for today. You do have an assignment in the online textbook, and it's just about conjunctions and counterexamples. You should have plenty of time to get this done during class today, but if not, it'll be open for, 3 days?